Sampling distributions for proportions. So a proportion or percentage of a population with a particular characteristic is represented in statistics by the parameter lowercase p. Gathering data from a population can be a bit daunting, so instead we get information from a sample, and we call this statistic p hat. So both of these represent proportions, just p hat comes from a smaller subset of the population. And there are a lot of samples that you can collect, so there are a lot of p hats that you could get. Each sample would have a different p hat or sample proportion. All the possible sample proportions that we could get from the population of a certain size will give us our sampling distribution. So for example, say we wanted to know the percentage of the population, the percentage of college students who are military veterans. What we want to get is the true population proportion. But there's probably a lot of college students in the United States, and so we're probably going to instead get a sample. So suppose that we survey 50 college students, which is a very small sample for such a large population, but if we survey 50 college students and out of those 50, 8 of them were veterans. Then our p hat, our proportion, our percentage, and it's p hat because it came from a sample of 50 rather than the whole population. So p hat is going to be 8 out of 50, which is 16%. But that was just one example, one sample that we took of 50 students. So let's say that the true population proportion of college students who are veterans is 10%. And let's continue to sample, get a p hat for a sample size of size 50. So this p over here, this 10%, has to do with the whole population of all college students, and our 50 students is our sample. And so what happened is I went out and I did this 100 times, and I took, I found a bunch of sample proportions, and noticed the shape of this, of all these p hats that I got. So these are various p hats, a percentage of college veterans. And notice the bell-shaped curve that forms after you repeat the experiment over and over again. And even more important, so our shape is bell-shaped. Our center, notice, look at where our center of this bell-shaped curve is, right on 10% there. And then the spread is pretty close together. This is what's going to happen, what we mean by a sampling distribution. If you were to collect more and more p hats, what you would see to happen. So you see that the 10% center here is the same as the population proportion of 10% there. So in this example, I looked at a population that had a percent of 30% chance of happening. So let's say 30% of college students watch Walking Dead. And then I went out and I sampled 50 college students over and over and over again. And every time I got a proportion. So right here, one time when I sampled 50 college students, I got that 48% of that sample watched Walking Dead. But that was rare. Most of the time, I saw around 28 or 30%. So, and then again, after 100 samples, I noticed that these p hats start to form a bell-shaped curve. It's not perfect. It's not pretty, but look at where the center is. The center is starting to get around that 30%, which is the same 30% of the population. So the p-hats, again, start to form a bell-shaped curve centered around the population proportion. So if 30% of college students watch Walking Dead, then 70% of them don't. So then I surveyed groups of 50, and 70% don't watch Walking Dead, but in some of my samples I got as low as 54% don't watch Walking Dead, and I got as high as 84% don't watch Walking Dead. But again, after 100 trials of size 50, I get a bell-shaped curve, and the center is right around that 70% of the population proportion. So we're noticing a pattern here, and for the next one, I bet you'll be able to guess where the center will be. So let's suppose that 50% of college students are men, and I'm going to have a sample size of 50. I'm going to do this over and over again. Where do you think my center is going to be? And your guess might be that the center is around 50%. And there it is, the center of this distribution. Again, roughly bell-shaped. We do have some, it's not a perfect curve, but it's pretty good for just 100 samples, each of size 50. Finally, in this example, what if I increased my sample size to 100? Notice from the last example, now this curve is very tight, close together, bell-shaped, centered right on that 50% of the population. So as I increase my N from 50 to 100, I notice that I get more consistent results in each of my p-hats. My highest sample proportion was 60% in one sample of 100 college students, and then my low was 38%. And so they're very close to the 50% of the population. So the question is, when are we guaranteed for this bell-shaped curve to happen? When are we guaranteed for that center to be the true population proportion? And there are some requirements. The first one is that the sample has to be a simple random sample. A lot of times in our homework and on a test, everything will be assumed to be a simple random sample. But the next requirement for proportion is that n times p, the number of successes, has to be greater than or equal to 10. N times q, the number of failures, has to also be greater than or equal to 10. And you might notice in some of the past examples we did that requirement wasn't met, and it still followed a roughly bell-shaped curve. But as soon as this goes into effect, what's called the central limit theorem takes place, and we start to see that pretty bell-shaped curve. And our p-hats, once all of these requirements are met, our p-hats will be normally distributed, centered on p, and the standard deviation we're guaranteed to be pq over n. And so once we have all these things in play, we know that this is going to be our sampling distribution for all possible p-hats. The last one says that n, the population size, must be significantly greater than the sample size. So n for the population has to be bigger than or equal to 10 times your sample size. So the moral of the story is, if we get all possible sample proportions, the distribution is going to be bell-shaped. And in fact, for proportions, it's going to be a normal distribution, and it will be centered on the true population proportion, P. So the center will be P, and then the spread, which we call the standard error of a sampling distribution, and we abbreviate it SE, standard error. That is given by the formula PQ over N. So as you survey more elements, your standard error is going to get smaller. Since as that N gets bigger, the standard error will get smaller. And so anytime you're working with a proportion and you have all those previous requirements in place, you will always use the z distribution to find what we call critical values. Critical values. So that's what's going to be on most of your homework for sample proportions. Enjoy.